Hello, this is Dr. Nair again, and we are talking about polar reactions in Chapter 6, which is our next topic. So, polar reactions occur because of electrical attraction between a positively polarized center and a negatively polarized center. Okay, and we can look at that on the functional groups of molecules. So, for example, we can see that this is a carbon-chlorine alkyl halide. There is a positively charged carbon center and a negatively charged carbon center, right? So in general, most of the organic molecules are electrically neutral, but as we have seen in the earlier chapter in the beginning of this section, chapter 2, that we can have polar covalent bonds where due to the difference in electronegativity, one atom can pull the electrons closer to itself, giving it a partial negative charge, and then that results in the other atom getting a partial positive charge. So this generally arises when we have elements like chlorine, fluorine, oxygen, nitrogen, which are more electronegative elements. Okay, and on the other hand, there are metals like lithium or magnesium, etc., which are more electropositive than the carbon, or in other words, carbon is more electronegative than these metals, and as a result of which you can see the direction of polarity is reversed now. So polar bonds can also result from interaction of the functional group with acids or bases. So for example, here we have methanol, which where the oxygen is slightly negatively charged and carbon is the positive center because of the difference in electronegativity. So that can react, the oxygen can behave as a base and take an acidic proton, as a result of which you can get what is called as a protonated methanol. Yes, this is also a very common type of reaction mechanism that we come across in organic reactions. So these are like acid catalyzed reactions, and similar examples we can see in base catalyzed reactions too. So if you look at this table here, we can see that some polarity patterns for some common functional group. Most of the examples are where carbon has a positive charge and the other element, which is like oxygen or nitrogen or sulfur, they have a negative charge. But then there are some examples here at the bottom where you can see that the polarity is reversed. Also, there is a phenomena called as polarizability, which is a result of an electric field around a given atom being changing, okay, due to some interaction with the solvent or other polar molecules nearby. So the measure of response of this response to an external electrical influence is called as polarizability of the atom. And larger atoms like sulfur or iodine, they have a higher polarizability because the electrons are much loosely held, and if they are smaller atoms, then like for example hydrogen or carbon, then they have lesser polarizability. They are less polarizable. In addition, we can also look at what are nucleophiles and electrophiles before we actually look at the mechanism of a polar reaction. Okay? We had studied earlier these two definitions in chapter 2 again, where nucleophile is something that is rich in electrons and electrophile is something that is poor in electrons. So when we show a reaction between an electrophile and a nucleophile, it's always the electron-rich nucleophile. The arrow starts at the electron-rich nucleophile and it ends at the electron-poor electrophile. So electrophile is electron-loving, and nucleophile is nucleus-loving. That's why the names are given as nucleophile being electron-rich and electrophile being electron-poor. So some examples of nucleophiles and electrophiles we can see here. Here every species that is shown here, they all are rich in electrons, so they are nucleophiles. And here at the bottom you can see that there is a electron poor area in each of this molecule, which becomes my electrophilic site. Okay, so it is the same molecule sometimes can have an electrophilic site and a nucleophilic site etc. Okay. So let's move on to maybe first show some examples to understand this. So for example, if I ask you which of the following can behave as a nucleophile and which as electrophile. So let's say if I have NO2 plus, okay, NO2 plus, this is a nitronium ion. So we see that since there is a positive charge, this is likely to behave as a electrophile because it's electron poor, right? On the other hand, if I take example like cyanide, okay, cyanide is Cn minus, where the nitrogen, the carbon is having the negative charge here, and nitrogen has a pair of electrons. Its valency is fulfilled, but carbon is the one that carries a negative charge, and here this will behave as a nucleophile. Now, in case of another example where I was saying that the same molecule can have nucleophilic as well as electrophilic sites, an example of that kind is CH3NH2, where you see that nitrogen is rich in electrons, so this part can act as a nucleophile. Okay, so we have this delta minus, and then carbon can act as a electrophilic site. Okay. So this is also very common examples where we see that the same molecule can behave either as a nucleophile or an electrophile depending upon the circumstances, depending upon with what it is reacting. Alright, so these are some examples of how to identify nucleophiles and electrophiles. Now let's look at a polar reaction mechanism, which is the one that is very common in most of the reactions that we are going to study. There are some reactions that are free radical, as we discussed in the previous video, but most of our reactions that we are going to talk about in the future chapters will be polar reactions. Okay? So this is a general reaction that's given. Ethylene is reacting with HBr. It's an addition reaction where the double bond opens up and H and Br get added to the double bond. Okay? So earlier we talked about different kinds of reactions. So this is a addition reaction of HBr to ethylene. So the mechanism of this reaction is described as where the double bond is now acting as a nucleophile because it is rich in pi electrons. Okay, we call it as this is a carbon-carbon pi bond, and it is weaker and it has got more accessible electrons. Electrons are more accessible here. Okay? But the sigma bond is not. So it is the pi bond that is making the carbon-carbon double bond a nucleophile, nucleophilic in nature. And then, so the mechanism is where the first step is the attack of the nucleophile to the electrophile. Okay, so maybe we can draw this a separate slide. So the first step is where the double bond, and we have the molecule as a very simple ethylene. As I said, this is going to be my nucleophile, the double bond and the pi bonds. It is reacting with HBr. Now, Br is more electronegative than hydrogen, so it pulls the electron towards itself, and we show a full arrow because it's pulling both the electrons towards itself, making this slightly delta negative, and at the same time the hydrogen becomes slightly delta positive. So here we have an electrophilic hydrogen, or something that is pouring electrons, and here we have a nucleophilic pi bond, right? So we have a nucleophile and an electrophile. Arrows are drawn always from a nucleophile to an electrophile. So this is my first step where the double bond opens up. So now I have a carbon with 3 hydrogen atoms. One of the hydrogen atoms is from my HBr. So maybe we can put a color there to identify. So this is the hydrogen that's coming from HBr. You can put a color to that. And the other carbon is now short of electrons, or its valency is not fulfilled because this pair of electrons has been used to form the bond with hydrogen. So this carbon gets a positive charge, and this intermediate species is called as a carbocation. Now this is step 1, and in the next step what happens is the carbocation is now reacting with Br minus. Now we have the electrophile again. Now is my carbon center here because it's poor in electrons, and the bromide, which was kicked out in the first step, that is going to act as my nucleophile, going to attack at this carbon, and it forms the final structure where we have the Br attached to this carbon, 2 hydrogens, and this carbon already has the all the valencies fulfilled, hydrogens. Okay, so this is how we describe the mechanism of this reaction in 2 different steps. It's all a nucleophile electrophile reaction. It's a polar mechanism, so everywhere we just draw the full arrows. You can clearly see that the first step is the formation of a carbocation, so it's a formation of a charged species, so this should be my slow step, okay, and the rate determining step, whereas the second step should be a fast step, because the intermediate really wants to get rid of the positive charge and have its valency fulfilled. So this is an example of a very simple polar reaction, and we see this kind of reactions very commonly in organic chemistry. If you see the mechanisms in a little more detail as the way the book describes, you can look at the carbocation structure. It has an empty p orbital because this is the carbon that is short of the pi electrons, because the pi electrons were used to form a bond with the new hydrogen. However, that makes this carbon electrophilic, and the Br comes and attacks that carbon atom to form the final product. So this is just one example of the polar process. We can try to do one more just to understand this better. Let's take a different alkene double bond again, okay? But here now I have a cyclic structure, and I do the same reactions, reacting with, say, HCl. Let's change the molecule HCl. Again, this is my nucleophile because my double bond is rich in pi electrons. Here the chlorine is more electronegative, pulls the electron towards itself, giving a delta negative charge, and hydrogen gets a delta positive charge. Here again, my arrow will be drawn from the double bond to the hydrogen formation of the carbocation in the first step. So this is step 1. We can show this double bond, or the pi electrons that are being used to form the bond, in a blue color. So both the electrons have been used to form the bond with the hydrogen, which is coming from the HCl. So here is my hydrogen. And so the other carbon atom, which is this one, is now short of electrons, so it gets a positive charge. So this is my first step in the mechanism. Second step, the chloride now goes and attacks the, so here I have my hydrogen, now I have the positive charge here, right? So the chloride, which was kicked out in the first step, that's going to attack at the electrophilic site, and then ends up in the formation of the final product. I have a hydrogen here and a chlorine here. Okay, so if you put back the color, this was the hydrogen that I took from the HCl, and then that chloride is getting attached to the carbon atom here. So these are examples of mechanisms of the polar reactions. Okay, so you have to really practice drawing arrow mechanisms. Practice using curved arrows in polar reaction mechanisms. Make sure that electrons always move in pairs. You cannot have single electrons move in polar reactions. That happens only in free radical reactions. And also the way the arrow is drawn is important. It's always from the nucleophile to the electrophile. So these are some examples. The tail of the arrow starts on the electrons, and the head of the arrow ends on the positive charge. Okay? Once you identify the nucleophilic and electrophilic sites, you have to make sure that the arrows are drawn correctly. We can practice maybe these are a few more examples in the textbook. Let's see. Yeah, here, see, it says fill in the necessary arrows for the reaction below. These are just for you to practice polar reaction mechanisms. We will come across these type of reactions in future chapters, but here you are only asked to draw the arrows to show the formation of the product. Okay, so when you look at the product here, you see that the carbon, this carbon here, right, this carbon here has a CH3 group, right? So that means my arrow should be drawn from the nucleophile. This is my nucleophile, and here this carbon is my electrophile. Why is this an electrophile? Because Br pulls the electrons towards itself because of its electronegative nature, and so gives this carbon a positive charge. So that makes this nucleophile attack this carbon atom. Okay, so it's always from a negative end to the positive. So that results in the formation of the product here, and then Br gets the electrons, so it becomes Br minus. Right. Now let's look at another examples. Here it's more asking you to draw arrows. Here again, if you see the nitrogen here, this is acting as the nucleophile, and then this chlorine atom, because of polarization, pulls the electron towards itself, as a result of which this chlorine here becomes delta positive. Okay, so nitrogen attacks the chlorine. That's how we get the product. And the second case, you are actually going this way. Okay? Again, the reason is Br is more electronegative, pulls this electron towards itself and creates a delta positive charge here. So that's why the nucleophile, which is my oxygen CH3O minus, it attacks the carbon atom. So the products. And finally, we have an example here, which is reaction is happening within the molecule itself. So you can see we have a double bond here. So the way we draw the arrow is from the lone pair to form the double bond, and simultaneously removing the it's not the CH3, it is the chloride that's getting removed. Okay, so simultaneously removing the chloride out. So it's a concerted reaction kind of, where you form the double bond at the same time chloride is kicked out. Okay, so that concludes my lecture on this polar reactions. But maybe practice some more worksheets based on this. The other two videos on part 2 of chapter 6 have been posted, so make sure that you watch all of them to understand complete chapter 6.